Affordances and constraints are fundamental concepts that shape how we interact with technology every day. These principles determine whether a digital interface feels intuitive or confusing, whether we can accomplish our goals efficiently or struggle with poor design. Affordances are the perceived possibilities for action that users identify in objects or interfaces. They represent what users believe they can do with something based on visual, auditory, or tactile cues. Let's look at some everyday examples of affordances. Notice how these objects communicate their intended use through their design. Buttons suggest pressing, handles suggest pulling, and stairs with handrails suggest safe climbing. Perceived affordances are particularly important in design. Objects like chairs suggest sitting, knobs suggest turning, and computer interfaces suggest interaction. The key is that users form these perceptions instantly based on visual cues. Constraints are the limitations that guide, restrict, or prevent user actions. Rather than being obstacles, good constraints help users by preventing errors and guiding them towards successful interactions. Here we can see how button states demonstrate both affordances and constraints. Different visual states communicate what actions are possible, while disabled states constrain users from taking inappropriate actions. In today's world of artificial intelligence and immersive technologies, understanding affordances and constraints has become more critical than ever. AI interfaces change dynamically, voice assistants rely on conversational cues, and virtual reality creates entirely new possibilities for interaction. Whether you're a designer creating interfaces or a user navigating digital experiences, these concepts help create technology that feels natural, prevents errors, and enhances human capability, rather than creating frustration. Affordances are the perceived possibilities for action that objects or interfaces communicate to us. They tell us what we can do with something based on the cues we receive through our senses. Visual affordances are the most common type we encounter. This button clearly communicates that it can be pressed through its raised appearance, bright color, and illuminated ring. The text and envelope icon provide additional context about its function. Tactile and haptic affordances provide physical feedback through touch and vibration. Modern devices use different haptic patterns to communicate various types of interactions, from light taps to deep presses, helping users understand what actions are possible and confirming when actions are completed. Modern digital interfaces combine multiple types of affordances to create intuitive experiences. Swipe indicators show gesture possibilities, voice assistants use audio cues to guide interaction, and AI systems provide contextual suggestions based on user behavior and current tasks. The iPhone's dynamic island demonstrates adaptive affordances perfectly. Its shape changes to communicate different interaction possibilities. A compact pill suggests a quick tap, while an expanded form reveals additional controls and information. The shape itself becomes the affordance. Are the limitations that guide, restrict, or prevent user actions in technology interfaces. Unlike affordances, which suggest what you can do, constraints define what you cannot or should not do, creating more intuitive and safer user experiences. Physical constraints are hardware limitations that physically prevent users from performing incorrect actions. The most common example is a USB-C connector, which can only be inserted one way due to its asymmetrical design. This prevents damage and ensures proper connection every time. Logical constraints are system rules that prevent actions that would be logically impossible or problematic. For example, operating systems prevent you from deleting files that are currently open in another program. This protects system stability and prevents data corruption. Cultural constraints are based on learned behaviors and social conventions that users understand from their cultural context. The color red universally signals stop, danger, or warning across most cultures. These constraints rely on shared cultural knowledge to guide user behavior without explicit instruction. Semantic constraints are meaning-based limitations that make logical sense within the context of the application. Calendar applications prevent users from scheduling events in the past because it would be meaningless. These constraints are based on the semantic understanding of what the application is meant to accomplish. These four types of constraints work together with affordances to shape user behavior and create intuitive technology experiences. By understanding physical, logical, cultural, and semantic constraints, designers can create interfaces that guide users naturally while preventing errors and confusion. Modern technology provides clear examples of how affordances and constraints work in practice. Smartphones and voice assistants demonstrate these principles through their intuitive interfaces and protective limitations. Smartphones excel at communicating possible actions through visual design. Every element on the screen provides cues about what users can do with it. Touch gestures demonstrate clear affordances. The raised appearance of buttons suggests they can be tapped. Swipe indicators show users which directions they can move. These visual cues make interactions feel natural and discoverable. Smartphones also use constraints to prevent errors and protect users. Grayed out options clearly show when features are unavailable. Confirmation dialogues prevent accidental deletions. These limitations guide users toward safe and appropriate actions. Voice assistants like Amazon Alexa create affordances through audio cues rather than visual ones. Conversational prompts invite users to respond. Different voice tones signal whether the assistant is asking a question or making a statement. Strategic pauses encourage user interaction. Voice assistants also implement important constraints for user protection. Wake word requirements prevent accidental activation when conversations mention the device. Privacy modes can disable certain commands when needed. Context-aware filtering prevents inappropriate content during family time. These modern examples show how successful technology balances user freedom with protective limitations. Smartphones and voice assistants make desired actions feel natural while preventing harmful or inappropriate interactions through thoughtful constraint design. Smart home devices represent a fascinating evolution in how we interact with technology in our living spaces. These devices use sophisticated affordances to make digital interactions feel natural and intuitive. The Google Nest Hub Max uses gesture recognition as a key affordance. Users can wave their hand to pause music, dismiss alarms, or control playback without touching the device. This creates an intuitive interaction that feels natural. Proximity sensors create another layer of affordances. When you approach the device, the interface automatically adjusts, showing more detailed information and larger touch targets. This contextual adaptation makes interactions more efficient. Moving into virtual and augmented reality, we see even more sophisticated affordances that blend physical and digital interactions seamlessly. Virtual and augmented reality interfaces, like the Meta Quest 3S, use hand tracking as a primary affordance. This allows users to interact with virtual objects using natural hand movements, making the digital world feel tangible. Spatial anchors are another crucial affordance in VR and AR. These allow virtual objects to maintain their position relative to the real world, creating believable interactions where digital elements behave according to physical laws. However, VR systems also need constraints to keep users safe. Boundary systems create visual barriers that prevent users from walking into walls or furniture. These constraints are protective, not restrictive. These examples show how modern interfaces blend physical and digital interactions. Smart homes use our natural gestures and movements, while VR creates entirely new interaction paradigms that still feel intuitive because they respect how we naturally move and perceive space. Artificial intelligence is revolutionizing how we interact with technology by creating dynamic affordances that adapt to our needs and intelligent constraints that guide our behavior in contextually appropriate ways. Modern applications use dynamic interface elements that appear and disappear based on what users are trying to accomplish. This finance application shows how toolbars and options adapt to the current task, presenting only relevant affordances. Predictive affordances represent another breakthrough in AI-enhanced interfaces. These systems anticipate what users want to do next and present relevant options before they're even requested. Emerging constraint patterns focus on progressive disclosure and contextual limitations. Rather than overwhelming users with all options at once, modern interfaces reveal functionality gradually as users demonstrate readiness for more complex features. Contextual limitations represent a sophisticated approach to constraints. These systems understand the user's situation and apply appropriate restrictions. For example, parental control systems that adapt based on a child's age, behavior patterns, and current context. AI systems also implement ethical constraints by refusing harmful requests while providing explanatory feedback. These intelligent limitations help users understand why certain actions aren't permitted, turning constraints into learning opportunities. These AI-enhanced affordances and emerging constraint patterns represent a fundamental shift toward more intelligent, adaptive interfaces that understand context, anticipate needs, and guide users toward successful outcomes while maintaining ethical boundaries. The future of interface design is moving toward three revolutionary approaches: contextual intelligence that adapts to user situations, inclusive design that works for everyone, and ethical constraints that protect user well-being. Contextual intelligence represents the next evolution in interface design. These systems continuously analyze user context to provide the most relevant affordances at exactly the right moment. Biometric authentication is just the beginning. Future interfaces will use location data to prevent dangerous interactions, monitor stress levels to simplify complex tasks, and recognize social contexts to adjust their behavior appropriately. Inclusive design is evolving beyond basic accessibility to create interfaces that naturally work for people with diverse cognitive abilities and sensory preferences. Modern inclusive design combines multiple sensory channels. Visual elements use high contrast and clear iconography. Audio provides voice guidance and meaningful sound cues. Haptic feedback offers texture and vibration patterns. Cognitive support includes simplified workflows and clear progress indicators. Ethical constraint design focuses on protecting users from harmful patterns while maintaining their agency and privacy. These constraints are designed to be helpful rather than restrictive. Ethical constraints include attention management features like usage limits and notification batching to prevent addictive behaviors. Privacy safeguards ensure transparent data collection, verify user consent, and automatically delete unnecessary personal information. These three pillars will define the future of human-computer interaction: intelligent adaptation to context, inclusive design that works for everyone, and ethical constraints that protect user well-being while preserving choice and agency. Understanding affordances and constraints is the foundation of creating technology that truly serves human needs. This knowledge helps us build intuitive interfaces while preventing misuse and confusion. For designers, this understanding transforms how we approach interface creation. Instead of adding features randomly, we carefully balance what users can do with appropriate limitations that guide their actions towards success. For users, understanding these concepts leads to more mindful technology use. When we recognize why interfaces work the way they do, we become more effective at achieving our goals and less likely to fall into design traps. The ultimate goal is to create technology that feels like a natural extension of human capability. When affordances and constraints are perfectly balanced, technology disappears into the background, allowing us to focus on what we want to accomplish rather than how to use the tool. By understanding and applying these principles, we create a future where technology truly serves humanity, where the interface becomes invisible and the possibilities become limitless.